So in this video, we're going to look at a very famous equation. E is equal to mc squared. In this equation, E stands for energy, m stands for mass, and c stands for the speed of light. This equation is sometimes called the mass energy equivalency formula. So what we can use it to do is convert between energy and mass. This is really useful when we talk about radiation because sometimes mass can be converted to energy. So it tells us if we convert mass to energy, how much energy can be created from that mass, and if energy is converted to mass, how much mass will be created from that energy. This is really just a follow on from the law of conservation of energy, which you've already encountered. It says that energy cannot be created or destroyed, only changed from one form to another. And the only difference with mass energy conservation is the fact that we're now counting mass as being a form of energy. So it can switch from energy to energy or energy to mass and vice versa. In a minute, we're going to have a look at a sample calculation using this formula. But before we do, I think it's important to have a look at what the different units that we're going to put in here are. So we're going to be using the standard units like with most physics equations. So energy will be measured in joules. Mass is going to be measured in kilograms. And the speed of light is going to be measured in meters per second. It's really important when we're going through these to keep these basic units in mind. And because we're dealing with atoms and nuclei and things like that that are very small in terms of their mass, and the amounts of energy be very small as well, and we have to be very careful that we don't use any units that we're given without checking first of all they fit in here. For example, with energy, you might be given the electron volt. So you can use your log tables to remind yourself that 1 electron volt is going to be equal to 1.602 by 10 to the power of 19. Sorry, minus 19. And for kilograms, instead of being given kilogram, you might be given the atomic mass unit. So again, it's important to remember 1 atomic mass unit is equal to 1.6605 by 10 to the power of minus 27 kilograms. Now, sometimes you may need to use more decimal places. Generally, a good guideline is to look at how many you're given in the question and use that as your base. But I think for these questions, because the numbers are generally quite similar, keep at least 4 decimal places, but more if you need to. So this is the first question we'll look at. It says if 8 mega electron volts of energy has been converted from mass in a reaction, how much mass has been converted? So straight away when we look at this, we know that we're dealing with the mass energy conservation formula. Because we're talking about energy being converted from mass. So we know that it's going to be E is equal to mc squared. That will be the main formula we're using here. Now, if we start looking at what will fill into this, we know that we're dealing with energy, and we're being given that. The speed of light we know is a constant, 3 by 10 to the power of 8. So we're going to be finding then mass is our unknown. Now, like I mentioned on the last slide, we have to be very careful that we are putting the correct units into the formula. So here we're given mega electron volts. We know it's mega and not milli because it's a capital M. So our mega electron volts we need to convert into joules. So we can check our log tables for this. And we will find out that 1 electron volt is equal to 1.602 by 10 to the power of minus 19 joules. So 8 mega electron volts is going to be 8 by 10 to the power of 6 electron volts, or 8 by 10 to the power of 6 lots of what's on the right hand side, 1.602 by 10 to the power of minus 19 joules. So really what we're doing is just multiplying the left hand side by this number, so then we're multiplying the right hand side by this number too, and that's maybe the easiest way to convert between the two. This gives us a final value of 1.2818 by 10 to the power of minus 12. You'll notice I added in a extra decimal place there at the end, just following my own advice of using at least 4 here. And then that gives us at least 4 decimal places in the answer as well. So now we have the energy given to us in joules. We're in a position where we can go back and fill that into the original formula. So we have the energy, we know the speed of light is, and then we can rearrange that to solve for mass. So if we fill in a new value for energy, it's going to be 1.2818 times 10 to the power of minus 12. Our mass is unknown, and the speed of light is going to be 2.9979 by 10 to the power of 8 meters per second. Again, we're going to use at least 4 decimal places here, but base it off the question too. If the question gives us more decimal places for a value, then we'll copy what the question gives us. So if we set about solving this, we will end up with the speed of light squared, which is going to be 8.9874 times 10 to the power of 16, and the energy on the opposite side will remain the same. Now to find mass by itself, all that we need to do is divide the energy, 1.2818 by 10 to the power of minus 12, by the speed of light squared, so 8.9874 by 10 to the power of 16. So when we do this whole thing out, the answer that we get to 4 decimal places is 1.2982 by 10 to the power of minus 28, and our answer is mass, so that's going to be in kilograms. Now this may seem like a really small amount of kilograms when we say 10 to the power of minus 28, but you have to remember that the amount of energy that was converted was already 10 to the power of minus 12, so already quite a small amount, but also any energy that gets converted into mass is going to end up as a much smaller number, because you're then dividing it by the speed of light squared. Now obviously it'll work the opposite way for converting mass to energy. The mass is going to be multiplied by the speed of light squared, but that's just something to bear in mind if you do end up with a number that seems really odd. Just check, well, were you putting in a very small number to begin with, and then were you dividing it by something very big, for example. So the next question we'll have a look at now is actually from the Physics Plus textbook. I think it's a pretty good question because it highlights the difference between atomic mass units and kilograms. So in this question they give us a nuclear reaction that happens. A proton collides with a lithium nucleus and it creates 2 helium nuclei, which we also call alpha particles, and it creates energy. Now what they want us to do is find the total mass before the reaction for part A. So we'll just have a look at that really quick. Before the reaction, we have a proton and we have a lithium nucleus. Now, if you recall, in your log tables, they actually have the mass of a proton written out in the table of constants. It's around page 46 or page 47. So the mass of that proton is 1.6726 by 10 to the power of minus 27 kilograms. Now you'll see here I've chosen to use 4 decimal places. You can use more if you want, or if the question seems to lead you to use more. For example, if there was 7 for use in the question, then I'd probably include 7 in my answer. But the reason we always include at least 4 in these questions is because the differences in mass are actually very, very small. So you might only see the difference appear down here, but you wouldn't see it in the first few decimal places. Now, we need to figure out what the mass of the lithium nucleus is as well. Now you can see that the lithium nucleus has a mass of 7 atomic mass units. Because we're dealing with really small changes though, we want to be a little bit more precise than that. So in a real leaving cert question, they will give you what the actual atomic mass of a lithium nucleus is. But instead, while we're doing these ones from the book, you can just Google what the mass is. So I Google the mass of lithium-7 nucleus, and that will give you your answer. So the mass is actually 7.016. So it's 7.016 atomic mass units. And we know that 1 atomic mass unit is equal to 1.6605 by 10 to the minus 27 kilograms. So we're going to multiply that by 7, and that will give us the actual value in kilograms. So again, this is the mass of the proton. You can just find that in the table of constants in the log table. This is how many kilograms there is in 1 atomic mass unit. But we actually have 7.016 atomic mass units. So we're going to multiply 1 atomic mass unit by this amount. When we multiply that out, we get 1.165 by 10 to the minus 26. And then we'll add that to the mass of the proton. This gives us a total mass before the reaction happens of 1.3323 by 10 to the power of minus 26 kilograms. Now I'm going to clear the whiteboard, but we'll hang on to this answer up here in the corner for the time being. Now we'll look at part B, where we need to find the total the total mass after the reaction. So to find this, we're going to get 2 times our helium nucleus's mass, because there's 2 of them that are created. And that's the only mass we'll find after the reaction. This arrow here just signifies the reaction taking place. For the 2 helium nuclei, it's actually very unlikely you'll be given its mass. And the reason for that is that they want you to realize that a helium nuclei is actually the same thing as an alpha particle when it's got a mass of 4, because that'll be 2 protons and 2 neutrons, or as we normally call it, an alpha particle. So again, they won't give it to you. They won't tell you what its mass is in atomic mass units. But you can look at the table of constants in your log tables and look for the mass of an alpha particle, and it'll give it to you there. So if you look it up in the log tables, it will say the mass of an alpha particle is 6.447 by 10 to the power of minus 27 kilograms. Now there are 2 alpha particles produced, so we're just going to multiply that number by 2. This gives us a final mass of 1.3289 by 10 to the power of minus 26. Our unit, of course, is kilograms. Now for part C, what they want us to do is calculate the amount of energy released. So to do that, what we're going to do is see what the mass changed by. So the mass beforehand was 1.3323 by 10 to the power of 26 kilograms. And the mass afterwards was 1.3289 by 10 to the power of minus 26 kilograms. You'll see now why it's really important that we kept 4 decimal places. Because if we kept, for example, 1 decimal place, well then our answer would be the same before and afterwards. And the same thing if we kept 2 decimal places, we get 1.33 here and 1.33 here. So that's why 4 is so important. So to find the energy released, we're first of all going to find the change in mass. So we'll subtract those two numbers from each other. So when we subtract them, we get a change in mass of 3.36 by 10 to the power of minus 29. Our unit here again is kilograms. Because we're dealing with kilograms, we know it's okay to put this straight into our formula. E is equal to mc squared. Now, we're trying to find the energy. We can fill in the mass. We can fill in the speed of light. So all that's left then is to do that and be able to solve for E, hopefully pretty easily. Okay, so we fill them in now. I think it's important as well just to note that we're using 4 decimal places for the speed of light too, just to increase our accuracy as much as we can. And that then will give us a final answer of 3.02 by 10 to the power of minus 12 joules.